In Illinois, 2.2 times 10 to the 7th people got their water from public supplies provided by cities and towns. Altogether, the people of Illinois used 1.1 times 10 to the 9th gallons of water each day. How many gallons of water per day did each person use? So that's the question we're trying to answer. How many gallons of water per day did each person use? Well, we know the total amount, the total number of gallons of water used by the people of Illinois, and we know how many people were getting their water from those public supplies. So, to figure out how many gallons of water per day each person used, we just need to divide the total amount of water by the number of people, and then we'll know how much water was used per person. So one way to show that division is to use a fraction bar. So I'll put the gallons of water on top, 1.1 times 10 to the 9th gallons of water, and divide that by the number of people, 2.2 times 10 to the 7th people. So when we complete this division and divide this top number by this bottom number, our answer will be the number of gallons per person. Now, but these numbers are both written in scientific notation. Remember, the front part of the number in the scientific notation, that's called the coefficient. So what we're going to do to complete this division problem without a calculator, we're going to start by just looking at the coefficients, and we're going to divide those. And I hope you can recognize when you look at 1.1 divided by 2.2 that this bottom number, 2.2, is just twice as big as the top number, 1.1. So 1.1 divided by 2.2 is actually equal to just 1/2, which as a decimal is just 0.5. So when we divide the coefficients, 1.1 divided by 2.2, we get a result of 0.5. Now, 0.5 is not the answer to this entire division problem, but it's a good start. Now, if we look at the powers of 10 that are a part of the scientific notation, now we can use one of our exponent rules. Remember, our quotient rule or quotient property tells us that if we are dividing two exponential expressions with the same base, we can keep the same base and simply subtract the exponents. So if I were just computing 10 to the 9th divided by 10 to the 7th, I would know that that would be equal to 10 to the 2nd, because 9 minus 7 is equal to 2. So putting those two pieces together, when we divided the coefficients and subtracted the exponents on the power of 10, we get a result of 0.5 times 10 to the 2nd power. Now, this number is almost written in scientific notation, although it's breaking one of our rules for scientific notation. Scientific notation requires that there be one meaningful digit in front of the decimal place, and 0 does not count as a meaningful digit. So this 0.5 as our coefficient really needs to change to be a 5, because the number 5 does have one digit in front of the decimal place. But we need to balance that change where we change 0.5 to 5. We actually increased the 0.5 by a power of 10 to move that decimal place to where it should be to create the number 5. So since we increased the coefficient by a power of 10, we have to decrease the exponent on the 10 by 1 to balance that. So we end up with 5 times 10 to the 1st power, and now we have a number that's in proper scientific notation. And remember, we are trying to figure out how many gallons of water per day each person used, and so that's what this answer represents. So 5 times 10 to the 1st power gallons per person. And that answers the question that we were trying trying to answer. Now, you might be thinking it's a little strange to write the answer or the number this way, 5 times 10 to the first power, because 10 to the first power is just 10, and 5 times 10 we can just do in our head, and 5 times 10 is 50. So for this problem, it might make more sense to express our answer in standard form, or 50 gallons per person. So, just to summarize a little bit, when we're dividing two numbers in scientific notation, we can divide the coefficients and really subtract the exponents on our 10 to get our answer. And then if we're supposed to write our answer in scientific notation, we have to make sure that our result here follows the rules for scientific notation. Or if we are asked to write the answer in standard form, we just need to move our decimal place and get our answer in standard form. So now on to the second problem. There are about 7 times 10 to the 9th people in the world. Suppose each person made 3 times 10 to the 4th dollars per year. How much money was made worldwide? So the question we're trying to answer, how much money was made worldwide? Well, we know how many people there are in the world, and then we're supposing that each person made this particular amount of money. So to get the amount of money made worldwide, we just need to multiply together the number of people by the amount of money that they're making. So I'm going to write this out as a multiplication problem. We have to do 7 times 10 to the 9th times, I think I'll use parentheses here to show the multiplication, 3 times 10 to the 4th. Now, those parentheses I put in really are unnecessary. I could rewrite this as 7 times 10 to the 9th times 3 times 10 to the 4th. And then we can change the order of things when we multiply. The order does not matter when we multiply, so I could group together the 7 times 3 and then group together those bases and exponents on the tens. So times 10 to the 9th times 10 to the 4th. And now we can see how to proceed here. The 7 times 3 we can just multiply together, and that's equal to 21. And then we know from our exponent rules that when we're multiplying two expressions with the same base, we can keep the same base, and then we add the exponents together, and 9 plus 4 is 13. So our answer is 21 times 10 to the 13th. Now, once again, this answer isn't quite written in proper scientific notation because this 21 for the coefficient is too big. Remember, we can only have one digit in front of the decimal place, and the number 21 has 2 digits in front of the decimal place. So I will need to change the 21 to a 2.1. In doing so, I'm taking this coefficient and decreasing it by a power of 10. So I have to balance for that by increasing by a power of 10 by increasing this exponent of 13 to an exponent of 14. So we have 2.1 times 10 to the 14th power. And let's make sure we remember the question we're trying to answer, how much money was made worldwide. So our answer should have a dollar sign attached to it. So our answer is 2.1 times 10 to the 14th dollars for how much money is made worldwide. That's our answer in scientific notation. If we wanted to express our answer in standard form, we could, but this is a problem where I think you can see that the answer is actually more easily written in scientific notation than in standard form. If I change to if I change to standard form, I would have the 2 and the 1, and then I would need to move that decimal place between the 2 and the 1 14 times. So I'd have to add a lot of zeros here. Let's see, I can move the decimal place once, but then I would need 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 zeros. Put my commas in place here. And this is dollars. So again, I think you can really see why there's an advantage to writing the answer in the scientific notation. It's shorter to write, and a number this long in standard form would be difficult to read out loud because it's not a familiar number to us, a number this large. So again, to summarize, when we multiply two numbers in scientific notation, we can just multiply the coefficients together to get kind of our new coefficient, and then we can add the exponents on the tens to get the new exponent on 10. And then once again, we might need to make some adjustments to this number to either change it to proper scientific notation or proper standard form.